chapter 3 is about systems of linear equations. So as before, in chapter 2, when we were learning how to graph and find equations for a single equation, now we're going to be looking at the graphs of two lines. So what is a system of linear equations? Well, an equation in the form ax plus bx equals c, ax plus by equals c are linear equations, right? We also express them in slope-intercept form. Okay, sorry, you can't really see that. We also express them in slope-intercept form. And if we're given two such linear equations, we call this a system of linear equations or a linear system. I primarily say system of linear equations. So a solution to a system of linear equations are the ordered pairs that satisfy both equations should such ordered pairs exist. So for example, if the two lines intersect, they will have exactly one solution. If the two lines are parallel, they have the exact same slope, they never intersect. That means there's going to be no solution. And if the two lines are the exact same line, that means that every single point on the line is the solution, and there are therefore infinitely many solutions because there are infinitely many points on a line. So, what are the solutions to graphs of linear systems in two variables? So first, if two graphs intersect into a single point, because the system has a solution, we say it's consistent. When something has a solution, we say it's consistent. The equations are not equivalent. They aren't related to each other, so we call them independent. If two graphs are parallel lines, this system has no solution, so we call it inconsistent. The solution set is the empty set. Remember that notation from a couple chapters ago. The equations are not equivalent, so they are independent. If two graphs are the same line, right, so there's infinitely many solutions, because they are the same line, every pair on the line is a solution, so it's consistent. Consistent meaning it has solutions. But the equations are equivalent, so they depend on each other. They just tend to be constant multiples. And I'll show you what that means in a little bit. So, for example, no solutions if lines are parallel. That means it's inconsistent. It's consistent, it has a solution. They're independent if they are not the same line. They're dependent if they are the same line. I thought this was a nice little visual I found on the internet. So, how do we solve a system of two equations? First, graph the first equation. Second, graph the second equation. If the lines representing the two graphs intersect at one point, determine the coordinates of their intersection, because that ordered pair where those two lines intersect, that's our solution. If the lines are parallel, there's no solution. If the lines are the exact same line, there are infinitely many solutions. And you always want to check your solution because it can be kind of hard to see them when graphing by plugging it into both equations, right? Substituting back in. So I've got x plus 2y is 2 and x minus 2y equals 6. That's my system of linear equations. So I'm going to go ahead and solve both of these for y, which by now we are such experts at. So I have y is negative 1/2 x plus 2. Sorry, not plus 2 plus 1. So much for being an expert, I guess. Just kidding. Because 2 divided by 2 is 1. So I've got where x is 1. Slope is rise over run. My slope is negative 1/2, so I'm going to go down 1 over 2. So here's my equation. Let's go ahead and find a bunch of points. So hopefully it'll be easier to identify where our two lines intersect. Now the equation for my second line is x minus 2y equals 6. I subtract x from both sides. Negative 2y equals negative x plus 6. I divide both sides by negative 2. So I get y is a positive 1/2 minus 3. So we go to negative 3. I go up 1 over 2 because it's a positive 1/2. Up 1 over 2. Ding, ding, ding. There you have it. See how clearly we can see where these two lines intersect? is that when x is 4, y is negative 1. Let me plug that in to our equations to check our answer. I have 4 plus 2 times negative 1 is 2. 2 is 2. That's correct. I have 4 minus 2 times negative 1 is 6. 4 plus 2 is 6. I agree with that. So our solution is 4, comma, negative 1. All right, let's look at some examples with no solutions or infinitely many solutions and how we denote those solutions. So we're going to go ahead and solve for y, which we are, like I said earlier, getting really good at. So I have y is 2x minus 3. And if you have any questions about how I'm solving for y, it'd be really good to go back and review chapter 2 and solving for y and getting an equation in slope-intercept form. So I've got y equals 2x minus 3. So when x is negative 3, my slope is 2, which is 2 over 1. So up 1 over 2, up 1 over 2. That's how I graph my first line. Let's go ahead and graph this second equation, but we're going to graph it in orange. As you can see, it's the exact same line. So there are infinitely many solutions. So our solutions are the set, right? So we're going to use set Boolean notation of ordered pairs x, y such that, remember that vertical bar means such that y equals 2x minus 3. So we have infinitely many solutions, every single point on this line. For this next example, again, let's go ahead and solve for y, and then we'll be experts at it. So I'm going to subtract 4x from both sides. 6y equals negative 4x plus 12. Divide both sides by 6. Y equals negative 2/3 plus 2 because we simplify our fractions. I subtract 2x from both sides. 3y equals negative 2x plus 4. Divide by 3. Y equals negative 2/3 x plus 4/3. So we can see that both of these lines have the same slope. Let's go ahead and graph our first equation. So when y is 2, my slope is negative 2/3, so I go down 2 over 3. So here's the equation for this first line. Next, in green, we'll go ahead and graph our second line, except my y-intercept is 4/3, which is a little bit more than 1. So here are two parallel, okay, wow. They're supposed to look parallel, these two parallel lines. They have the same slope, there's never going to intersect, so there are no solutions.